What is natural language processing? Well, it's a sub-area of computer science that includes problems and solutions related to human language. We can think of NLP problems as being in three categories. First, we'll talk about user-facing applications. These are the kinds of things we use every day. One simple example is text classification, which shows up in a lot of places. For example, email software detects spam, determines priorities, and classifies email to categories like promotions and updates. Next, text completion or autocomplete. This first became popular when writing text messages on mobile devices, but now we use autocomplete technology in lots of settings, including writing email, as in this example. Another widely used application is machine translation, one of the oldest problems studied by artificial intelligence. It's widely deployed and used, but still an active area of research. Finally, there are many personal assistant and question answering systems like Siri from Apple, the Google Assistant, and Amazon's Alexa, among others. These are increasingly being used as interfaces to a wide range of NLP capabilities, including open domain conversation, which covers pretty much anything. What about things like speech recognition and web search? These are studied by NLP researchers, but they also have their own dedicated research communities. While we won't talk much about speech in this course, we will touch upon web search a bit, as it has seen more interaction recently with NLP, especially for answering complex questions like this one. Those are just a few of the many NLP technologies that have become a part of everyday life. The second category are problems that are not user-facing, but may be able to help us design better solutions for the user-facing applications. First, part of speech tagging, where the goal is to label each word in some piece of text with its part of speech. For example, girl is a noun, walked is a past tense verb, and so on. There are also several forms of syntactic parsing. This is constituency parsing, where in addition to part of speech tags, we want to find and label constituents and connect them in a hierarchical structure. For example, the girl is a noun phrase, and walk to the park is a verb phrase that consists of a past tense verb followed by a prepositional phrase, which in turn contains a preposition and another noun phrase. Another form of syntactic parsing is dependency parsing. Here, instead of finding constituents, we want to identify for each word which word it modifies or depends on. Typically, the root of the tree is a verb, and then arguments like the subject depend on the verb. We also use dependency relation labels to indicate the type of relationship that is captured by each dependency. There are several types of semantic parsing as well. One type is called semantic role labeling, where the goal is to find a predicate, like gave, as well as its arguments. Who was doing the giving, what were they giving, who were they giving it to, as well as when and where did the giving take place. Next is coreference resolution. Given a document, the task is to find and cluster mentions that refer to the same entity, for example, a group of birds and they. In named entity recognition, the goal is to find and categorize mentions of entities in text. Here, Microsoft is an organization, Bill Gates and Paul Allen are persons, and so on. Now we'll move on to our third category. These are not user-facing, and we're not even sure that they'll be helpful for any user-facing applications. But we study them because they can help us to assess how well our systems are understanding natural language. One example is Winograd schemas. These are coreference resolution tasks that are especially designed to require world knowledge or reasoning to be able to solve. These two sentences differ by only one word, yet that word changes the referent of he from the man to his son. Reading comprehension question answering is another such task. Here we have a short story about a boy named Fritz, as well as multiple choice questions that test our understanding of the events in the story. Another task is natural language inference. Here we have a pair of sentences, A and B, and we want to classify the relationship between them. For example, if I say that yesterday's game was canceled because of the heavy rains, that entails that it rained yesterday. Other commonly studied relationships include contradiction and neutral, and here are some examples of those. Okay, we went through a lot of different problems in NLP, and we'll see many of these in more detail later in the course. But now how about solutions? Here's a brief history. The classical NLP period, starting around the 1960s, was characterized by linguistic theory, a lot of manually defined rules, and any empirical component was on a small scale. The statistical revolution began in the late 1980s, led by IBM researchers who had found success in using data-driven methods for speech recognition. These methods were soon being used for machine translation, parsing, and lots of other tasks. The standard approach became supervised machine learning with manually annotated datasets. Models were fairly simple, mostly linear models with a lot of handcrafted features. And there was a lot of work in incorporating linguistic knowledge, whether in data annotation, feature development, evaluation, etc. The current paradigm is neural NLP, learning representations of language from large corpora with deep neural networks. There's much less handcrafting of features or use of linguistic structure. In the course, we'll be covering a variety of methods from both the statistical and neural eras of NLP. Why is NLP hard? Well, natural language data poses many challenges for computers. One challenge is ambiguity. One linguistic form can have multiple meanings depending on context. Another is variability. Multiple forms can have the same meaning. Here's one example. We'll see many more examples throughout the course. If you look at hyperlinks with the link text bar in Wikipedia, you'll find links to many different Wikipedia articles depending on which sense of bar is meant in the context. At the same time, if you look at all the links to the bar establishment document, you see a wide variety of link texts. Humans can handle these challenges effortlessly when using natural language. You might not even be conscious of the many meanings for a particular form because your brain hones in on the most appropriate one so quickly. But for computers, these sorts of things are much more difficult. A question often arises, what's the difference between computational linguistics and natural language processing? While some people use these terms interchangeably, computational linguistics is more likely to include things like sociolinguistics and computational social science. NLP tends to be more focused on machine learning and system building to solve a particular task. Next, we'll be discussing words, tokenizing text into words, handling word structure, representing word meaning, and dealing with multiple word senses.